Hello, friends. This is a video on electric fields. This one's pretty straightforward. I'm just going to do the quick notes, and we're going to practice this in class. So, electric field, otherwise known as E field. So, if the whole idea is this, is that what's observed in the universe is that opposites attract, opposite charges attract, and like charges. What does that mean? That means if you have a positive and a negative, they will experience a force called the electric force toward each other. And if you have two negative charges or two positive charges, they will experience an electric force away from each other. The whole point is that, right? Charge A creates a field. We'll call that E sub A. Charge B, which is any charge that wanders into that field. Now, this field exists. If there was one charge in the universe, it would create a field that points outward in all directions, that gets weaker with distance. And that field would exist and then do nothing. It would be a meaningless field, just in and of itself, it exists. Now, if another charge wanders into that, by the way, for charge, we use the letter Q. So Q is charge. E is electric field. Careful, it's not F. It's E. Please know this very well. Please don't come to class 2 weeks later saying, what is E? E is electric field. This is step one. What does this mean? So Q is charge, Q, or little q. Sometimes we'll do a little q. So if I have a little q coming into here, say we have another positive little q coming into here, it'll experience a force outward. The reason it experiences a force outward is because the field points outward. So the field feels a force, which we call Fe. So this is EA. The charge A creates a force due to the field. If you get this, you get field theory. This is step one. This is the concept. The concept is, and this is actually remarkable, guys. This is like the meaning of existence. This is like going into like the nature of reality, is that object one creates a field. Everything is fields, guys. It's extraordinary. We're going to get into this. This is step one, electric fields. Great way to introduce this concept. Charge A creates a field, charge B feels a force due to the field of another object. So a few things to go over. One is a charge never feels its own field. Right? And so, but each charge feels the other's field. Feels every other field in existence, really. Actually, I mean, obviously, if there's in real life, there's almost countless charges exerting fields on each other, and the ones that are close by will dominate. But technically, we're feeling the gravity from Jupiter. Technically, every electron's feeling the field from every other charge in existence. And it's just the ones that matter are the ones that are close by. So we'll do 2 or 3 at a time in this class, but really this field theory is this combination of every other field in existence is affecting every single charge. But a charge never fills its own field. Each charge fills every other field in combination. We call that superposition, which is just the sum of all fields. That's the sum of E sub I, just meaning E sub I, meaning I counting from however many charges you have. So I equals 1 to however many n, right? Don't worry, this is just a mathematical way of saying you add up the fields, which we're going to do. I'll show you what this means physically, much more important, what this means. And these are vectors. Great. So step 1 is this, but step 1 mathematically is that, okay, say I have some point, I know, so I had charge 1, I should have called it charge 1. I'm gonna get this. Charge 1, charge 2. Sorry to erase and read. It's gonna fit with my notes a little better. Charge 1, and then charge 2 feels the force. So this is 1, and that makes a little more sense. I equals 1 to n. Let's say we have a point A in space. So charge 1 is here, it's creating a field. And I put another charge. So the concept is this, the E field points in the direction that the test charge, sorry, it's not necessarily positive, that Q feels an electric force. So it points in the direction of the electric force. So if this charge is positive and this charge is positive, then the force will point outward. Therefore, the field points outward. The convention is that actually, sorry, it is, sorry, I didn't mean to draw that. It points in the direction that a positive charge feels a force. So say I want to know what the field looks like around this charge. What I do is I pretend, these are called test charges. Remember, the field exists without anything in it. It's like a conveyor belt without anything feeling it. Right? The air exists until somebody comes and breathes it, right? So the field exists without anything feeling it, waiting, right? Waiting for something to drop in. So if I dropped a test charge in and I said, which way would it go? Well, you would tell me it repels. So it points out. But that means that due to this, right, the electric field points away from this positive charge. So E1 will point away. I'm trying to draw away from this charge. No matter where I put this positive charge, it's going to go away. So let's draw this a little more accurately. So let's say I have a positive charge here, Q1. Let's say I have a negative charge here, Q1. Let's compare. If I throw in positive test charges here, close and far, and I'll do the same here. Do one out here, do one out here. Great. What we see is that the force points away from the positive, but the force points toward the negative. So what does that mean? That means electric fields point away from positive and toward negative. So an electric field will always point out of positive charges, and electric fields will always point into negative charges. You can kind of just memorize that, but it comes from this convention that the electric field points in the direction a positive test charge feels an electric force. So it's the same vector direction as the electric force. So I usually say, remember, out of positive into negative. That is the direction of E. Remember, E is different from F. Now, they're related. So you might say, but I thought they were the same thing. Isn't the E field the same as the electric force? Well, no. It almost is exactly the same thing. Here's the trick. Let's do an example. I have a positive charge here. Great. It creates a field that points out. Great. We're going to want to mathematically describe that. We will in a second. But first, the concept. Say here I have an electric field. This is a point A in space. Say I have an electric field that points outward. Call that E1. Say E1 has a value of, we're going to see the unit is newtons per coulomb. Say it is 10 newtons per coulomb. Oh yes, by the way, the unit of charge is a coulomb. What is charge? Charge is the quantity that creates and feels electric fields. It's the necessity to interact with the electric field. And therefore electric force. So, but it's all about the field. So say I have that. Let's put a positive 1 coulomb charge there. If I put a positive 1 coulomb charge there, it feels a force in that direction. Of what value? Well, the force is the charge that feels the field times the field strength. So the bigger the charge, say I put 2 coulombs here, right? And this is also a field of E1 is 10 newtons per coulomb. Then this one is going to feel a force. Let's draw it a little more accurately. This one's going to feel a force outward. And this one's going to feel a force outward, but this one's going to be a bigger force because it's a bigger charge feeling it. So the bigger, it's like a heavier thing weighs more, right? I know they both accelerate the same because the acceleration depends on mass, but the force depends on the charge, just like force depends, like something's weight depends on its own mass, not just the mass of the Earth. If that makes sense. The analogies are very apt with gravity, except we're using charge instead of mass. So, for instance, the force on, we'll call this charge A, and we'll call this charge B. The force on 1 coulomb is going to be positive 1 coulomb times 10, which is 10 newtons. And you can see here why the unit of E is newtons per coulomb, because if we do newtons divided by coulomb, we get electric field. There is no special unit for electric field because newtons equals coulombs times newtons per coulomb in this equation. Right, so the force on the 1 coulomb charge is 10 newtons. The force on, let's see if I can squeeze it in here. Force on positive 2 newtons will be, of course, 2 times 10, which is 20 newtons. So you can see that the bigger the charge that's feeling the field, the bigger the force. Now, part 2. Say I have some negative charge causing the field. So please caution. Right? Know what charge is causing E and what is feeling. Now, any charge causes, and therefore Fe. Any charge causes an electric force, all of them do, but we're only considering one at a time. So we'll say, consider this as the, we call this the source charge. And then we call this the test charge. Any charge can wear the source charge hat, right? And say, we're considering this is the source and wondering what field it creates and how it affects everything around it. And then we'll switch to this other charge and say, now, how is this charge acting as a source charge as well? So remember, a charge never feels its own field. So we can just go from one to the other and say, what is this doing to the universe? So caution, know what is the source charge and what is the test charge. So let's say I have a source charge that's negative, and it creates an electric field that points inward like this. Let's say here at point A, I have an electric field of, again, 10 newtons per coulomb. It's not negative, it's just a value. So the electric field will be 10 newtons per coulomb down to the left, down and left. So if this is negative, that doesn't mean that the electric field is negative, because look, here the electric field points to the left, but here the electric field points to the right. So remember, we use a vector orientation, right? Up, down, left, right. We have a coordinate system. We have to choose positive and negative directions based on up, down, left, right, not based on the charge itself, which means the electric field value is only dependent on the magnitude of the charge, not the sign of the charge. We're going to mention that in a second. That's really important. Rewind that if that didn't make sense. Play that over. That was really important, right? EA, say, is 10 newtons per coulomb. I'm just making up numbers here, just to give an illustration, down to the left, whereas here was up and to the right. So that we would plug in there, but let's say we have a negative test charge as well. Let's throw a -1 coulomb charge in. What's that going to do? Well, if I have an electric field pointing down and to the left, and I have a negative source charge, sorry, a negative test charge. Well, here's the point. Negative charges feel the force in the opposite direction, right? What does that equation say? F as a vector is Q times E as a vector. So if this is negative, if little q is negative, then Fe is negative E in direction. Right? So this negative will manifest as Fe is going to be -1 coulomb times -10 newtons per coulomb, which is -10 newtons. But what does the negative mean? Negative will mean up and right. Negative just means opposite what E was, right? So negative is going to mean it's going to go this direction if we chose this as positive. Now, if we chose this as negative, then Fe will be positive. It's the whole point is it's just a negative vector, which we should be okay with and understanding now. We should be comfortable with that. I hope that we're comfortable with negative vectors. All they mean is opposite direction. We've encountered this a few times so far. Hope it makes sense, right? So what's the summary? Positive test charges versus negative test charges. First of all, positive source charges, electric field goes out. Negative source charges, electric field goes in. It's not a positive E or a negative E. It's just out and in, because here's left, sorry, here's right, here's left, here's left, here's right. Be careful. So out of positive into negative, right? E is positive or negative depending on choice of coordinates. As we're all good at doing, taking power over our coordinate systems. Now, if the test charge feeling the field is positive, sorry for my scribbles here. If the test charge feeling the field is positive, I'm making it worse. I don't know. Good enough. It makes sense. Feeling field is positive. then FE is same direction as E, which we already knew because that was the definition. That electric field points in the direction of positive charge field. So that's by definition. That's literally how this is defined when this was first created as a model that the people did. I'll throw out some names. Coulomb, Maxwell, Faraday, the people who worked on these. Negative charge, Fe is opposite to. So negative charges just go the opposite direction. Now here's the last point. If I have a test source charge, that field is spread out over a bigger and bigger area of a sphere. An area of a shell is 4 pi r squared. So the area goes down as r squared. So as I go bigger and bigger out, it gets spread out, it gets diluted, which means the electric field is given by something we call the electric constant times the absolute value of the charge over r squared. And K is actually 1 over 4 pi epsilon naught, where epsilon naught is called the permittivity of free space. So I'm scribbling this permittivity of free space, which represents how effectively the electric field goes through space. So they've put this 4 pi in here. Notice that should be 4 pi r squared in the bottom. So it's the electric source divided by the area of the shell. Isn't that cool? Right? So it goes down as r squared. So if I have positive 1 Coulomb charge and I'm 1 meter away, the electric constant is enormous. It's 9 billion, 9 times 10 to the 9 in units that make this work. So newtons per Coulomb squared meter squared, something like that. So 1 meter away, I get an electric field that points out. So E at point A will point out 9 times 10 to the 9 times 1 Coulomb over 1 meter squared. And of course, that gives me 9 billion newtons per Coulomb. That's enormous. What this shows us is how big a Coulomb is. There is nothing here but the field. Nothing is there but the field, right? That's really important, that only the field exists until a charge wanders in. And if I put a little charge in there, say I put a -1 nanocoulomb charge in there, then it feels a force inward because it's opposite, it's negative, and the force on the -1 nanocoulomb charge equals -1 times 10 to the -9, that's nano. Remember nano for -9 times 9 times 10 to the 9. You see why I chose that? Because the 9 and -9 cancel and I get -9 newtons, but -9 just means left. Whereas the electric field was to the right. So E is field, F is force. Field creates force, but only when a charge is there. So be careful of the difference between field and force and whether the source charge or the test charge are positive and negative. And already you're probably like, man, that's a lot to keep track of, but that's electrostatics. That's what we're doing here. That's the end. Please rewind if you need to. I hope that made sense. I'll see you guys in class.